All right, greetings, YouTube. Beautiful mind here. Welcome back. Happy New Year. Congratulations, you survived 2021. So this is going to serve as a lecture for our Calculus for Business course for spring of 2022 at Morehouse College, right? And my goal or the intent, I'd like to get through chapters 1 and 2. Like I want to have two exams and a final. Exam 1 is during week 6. Exam 2 is during week 12. And then we have a comprehensive final. For exam 1, I'd like to get through chapters 1 and 2. And then for exam 2, I'd like to get through chapters 3 and 4. All right. The pace might be a little bit intense, and I'll try to like compensate by dialing back on the amount of work I give. It's very easy to give a good amount of work here, and I'm not trying to overwhelm you. I just want to kind of introduce these concepts to you, and like let's just kind of talk about the stuff and get some practice with these. Now, I don't really want to go too in depth. I just want to kind of like do the best I can to try to introduce and touch on ideas and notions. So with that, we're going to start with chapter 1 on differentiation, and start with section 1.1, limits, a numerical and graphical approach. The objective here is to find limits of functions if they exist using numerical or graphical methods. So for this example, we're asked for each sequence, determine its limit and rewrite the sequence in the form x. The limit is x approaches a coming from the left and x approaches a coming from the right. So you might notice this minus and this plus that look a little bit weird or look a little bit unfamiliar to what you're used to. The minus just means as x approaches that number coming from the left, and that plus just means as x approaches that number coming from the right. So if we look at part A, the first number in the sequence we have 2.24, and then 2.249, and then 2.2499, and then 999, and so on and so on. So then this limit is going to be 2.25. Is going to be the limit is going to be as x approaches 2.25 coming from the left, right? Because these numbers are smaller than 2.25, so these are approaching 2.25 from the left. If we look at part B, we have 5.51, and then 5.501, and then 5.5001, and then 0001. You could do quad 01, so on and so on. So this one is x is approaching 5.5, but coming from the right side. So coming from the right, this is going to have a plus in it. And then for part C, the first number is a half, and then 3/4, 7/8, 15/16, 31/32, 63/64, so on and so on. So these numbers are getting closer and closer to 1 coming from the left. All right, so this is x approaching 1 from the left. Okay. So for part A, these numbers are approaching the limit 2.25. Since each number in the sequence is less than 2.25, we write x approaches 2.25 from the left. Again, x approaches 2.25 from the left. For part B, these numbers are approaching the limit 5.5. Since each number in the sequence is greater than 5.5, we say x approaches 5.5 coming from the right. Again, it's red, x approaches 5.5 from the right. Okay. And in part C, these numbers are approaching the limit 1. Since each number in the sequence is less than 1, we write x approaches 1 from the left, red, x approaches 1 from the left. Okay. So let's introduce this definition. As x approaches some number a, the limit of f of x is L, written x approaches, the limit as x approaches a of f of x is L. If all values of f of x are close to L for values of x that are sufficiently close to but not equal to a. So basically the limit, with limits, we're just concerned with what happens as we get close to some number. We're not so much concerned with the value at that number when we're talking about limits. Limits we're most are concerned with on either side of that number. As we get close coming from the left and as we get close coming from the right, what happens? So we have this theorem. It says that as x approaches a, the limit of f of x is L if the limit from the left exists and the limit from the right exists, and both of them are the same number. So again, the theorem is the first part, the limit as x approaches a from the left is L. The limit as x approaches a from the right is also L, then we say the limit as x approaches A exists and is L. So for the limit to exist and to be defined, the limit on the left has to equal the limit on the right. Okay? So we have a quick check. Given this function, what is f of 3, right? So if we plug in when x is 3, I think we get a result of 0 over 0. You know, it's indeterminate or not defined or whatever. So then the second part says, what's the limit of f as x approaches 3? So now with this one, we're concerned with how does this function behave as we get close to 3 coming from the left and as we get close to 3 coming from the right. So the first way we're going to introduce to kind of evaluate this or analyze it is through a table. We're just going to look at table values of x and get them closer and closer and closer to 3 and see is the y value approaching some number. Okay, so if we just plug in x equals 3, we get 0 over 0. So it's not defined when x is 3, right? That was part A. So then for part B, so now we want to consider as x approaches 3. So first we're going to consider as x approaches 3 from the left. So left to 3, so we just chose x is 2. There's the corresponding y. When x is 2.5, corresponding y. Now we got 2.9, 2.99, 2.999, so on and so on. So then it should be clear that as x approaches 3 from the left, f of x approaches 6. And then we want to consider the limit as x approaches 3 from the right. So we just chose 4, find the corresponding y. We chose 3.5, corresponding y. 3.1, then 01, and then 001, right? So the limit as x approaches 3 from the right is 6. Since both the left hand and right hand limits agree, the limit as x approaches 3 of f of x is 6. Right? So we evaluate it on the left and evaluate it on the right. Consider this function. Graph the function and find each of the following limits if they exist. When necessary, state the limit does not exist. All right, so we have part A and part B. Part B is concerned with the limit as x approaches 1. The limit as x approaches 1 of this piecewise function. So say we're approaching 1 coming from the left, right? We want to start by choosing numbers that are smaller than 1. So then if we're going to choose numbers smaller than 1, are we going to use the first line or the second line? Right? So we should be using the first line. So if you choose values of x like you can do 0 and then a half and then 0.9 and then 0.99 and then 0.999 and then 0.999, right? You should find that those y values should get closer and closer to 4. Coming from the right, we might choose numbers like 2 and then 1.5 and then 1.1 and then 1.01 and then 001 and then so on and so on. As we approach 1 coming from the right, we should get -2. Right, so I think the first one we got 4. So coming from the left, we get the limit is what? 4. Coming from the right, the limit is -2. So because the left-hand limit does not equal the right-hand limit, for part A, we're going to say the limit as x approaches 1 does not exist. Right? And then for part B, as x approaches -3, now for -3, we're just going to be using line 1. Because as we're approaching -3 from the left, you would choose like -4, -3. -3.5, -3.1, -3.01, so on and so on. So let's see this in action in table form. So for part A, the limit as x approaches 1 from the left, they chose 0, found the corresponding y's for these. Notice the y values are getting closer and closer to 4 from the left. From the right, so they chose 2, 1.8, 1.1, 01, so on and so on. The y values are getting closer to -2. Right? So then for part A, I think we already acknowledged this. The limit as x approaches 1 from the left is 4. The limit as x approaches 1 from the right is 2. So therefore, the limit as x approaches 1 of this function does not exist because the left-hand limit is not equal to the right-hand limit. Okay. So then in a graphical sense, so as x approaches 1 from the left, the corresponding y coming from the left is approaching, what is this, 4. Coming from the right, the y value is approaching -2. So because they're approaching different numbers, we say the limit does not exist. Okay. So you have to bear with me. This is like my second time doing this presentation. The first time I did it, and then I guess I clicked something wrong, so it made it display improperly. So that was like 30 odd minutes. And so like now I'm kind of like burnt a little bit. I want to go to sleep so bad. But I was like, well, I want to finish this just to have a clean run, because that's just what I want to do. So then the limit's numerically, right? So for part B, we were considering -3. So we want to see, okay, the limit as x approaches -3 from the left, right? So we chose -4, -3.5. For all of these, we're finding the corresponding y, and we're getting closer and closer to -4. As we approach -3 from the right, they chose -2. Find the corresponding y's of these, and it's still approaching -4. So then for part B, because the left-hand limit, the limit as x approaches -3 from the left equals -4. The limit as x approaches -3 from the right equals -4. So then the limit as x approaches -3 is -4, because the left-hand limit equals the right-hand limit. Okay. And then in a graphical sense, you can see x being -3 over here. Coming from the left, y is approaching 4. Coming from the right, y is approaching 4, or -4, right? Okay. So in this example, we're asked to calculate the following limit based on the graph of the function. The limit as x approaches 2 from the left. So as we're coming from the left, the y value is getting closer and closer to what, 3? 2 from the right, the y value is getting closer and closer to 3. So then the limit as x approaches 2, we say the y value is 3. Even though this function is not defined when x is 2. Right? So remember, limits, we say that we're not really concerned with the value at the point. We're more so concerned with when we're close to a point. Okay, and here's just a typed version of what we just said. So then another technique, you kind of saw me do it. I kind of did it a little bit just a moment ago. It's called the wall method, right? So as an alternative approach to example 1, we can draw a wall at x equals 1, as shown in blue in the figure on the following graph. We then follow the curve from left to right with a pencil until we hit the wall and mark the location with an X, assuming it can be determined. Then we follow the curve from the right to the left until we hit the wall, and we mark that location also with an X. If the locations are the same, we have a limit. Otherwise, the limit does not exist. Okay. So in example 1, so when we were considering x equals 1, you can see the wall. We have a blue wall here. As we trace left to right, the y value hits the wall at a value of 4. As we trace right to left, the y value hits the wall at a y value of -2. So because the left-hand limit does not equal the right-hand limit for part A, that's why we said the limit does not exist. For part B, we were concerned with x approaching -3, so we put a wall at -3. Coming from the left, the function hits the wall at a y value of -4. Coming from the right, the function hits the wall at a y value of -4. So then, because the left-hand limit equals the right-hand limit, we say the limit as x approaches -3 is 4. I know that was a little bit fast. Okay. Let's try another one. So consider the function given by this. We're asked to graph the function and find each of the following limits if they exist. If necessary, state that the limit does not exist. So the limit as x approaches 3, right? So we're just concerned with, okay, as we get close to 3 coming from the left and as we get close to 3 coming from the right, what are the y values getting close to? And then for part B, I think we're just going to use a table here for both of these. The limit as x approaches 2. Notice we can't just plug in x equals 2 because we get a 0 in the denominator. But x approaches 2 means we're just concerned with as we get closer to coming from the left and the right. Let's look at the presentation. So as x approaches 3 from the left and the right, so these y values are getting closer and closer to 4 coming from the left. Coming from the right, the y value is getting closer and closer to 4. So therefore, the limit as x approaches 3 of this function is 4. And you can see the wall method. We were concerned with as x approaches 3, so you put the wall at 3. As we trace it left to right, it hits the wall at a y value of 4. As we trace it right to left, it hits the wall at that same location. So then we say that's the limit as x approaches 3 from in general. But then as x approaches 2 from the left, now if we make our table, from the left of 2, we would choose x values of like 1.5, 1.9. These guys will find the corresponding y's. So the closer and closer we get to 2 from the left, the y values go off to negative infinity. The closer and closer we get to 2 coming from the right, the y values go off to positive infinity. So therefore, the limit as x approaches 2 does not exist, right? Okay, let's try another one. So you can see it in a graphical sense. As we approach 2 coming from the left, y goes to negative infinity. As we approach 2 coming from the right, y goes to positive infinity. So therefore, the limit as x approaches 2 does not exist. Okay. So with this example, it says, consider again the function given by this. Now we're asked to find the limit as x goes to positive infinity, as x goes off to the far right. So as we choose bigger and bigger values of x, right? So I think we're still going to make a table and look at the table of points, but I just want you to kind of consider the following. Like, what happens to this expression as x goes to positive infinity, right? So for instance, when x is 3, we get something like that expression goes to 1. When x is, say x is like 102, it gets bigger, or 12. So then this is going to become 1 over 10. Say x were 102, then this is going to become 1 over 100, right? What do you notice is happening? The bigger and bigger we make x, what do you notice happening to this expression? We have a fixed numerator and an expanding denominator. So the bigger and bigger that denominator gets, this whole thing goes to 0, leaving us with our limit, right? That was just a concept, but we could still evaluate this with a table, right? So if we're approaching infinity, we might choose values like 10, 100, 1,000, 10,000, find the corresponding y values. All right, let's see. So they chose, if we're considering x goes off to infinity, they chose 5, 10, 100, 10,000, and they just found the corresponding y for each of those. So what it looks like is the bigger the x gets, the closer y gets to 3. All right. So I think this is like a one-sided limit or an infinite limit. Okay, sorry. Like I said, I literally just did all this. It took me like 30 odd minutes, and then I realized I just made a mistake in the setup, so I had to do it all over. Graphically speaking, with that last one, notice as x goes off to positive infinity, y gets closer and closer to 3. Okay. Let h of x be this. Find the following. The limit as x approaches 1. So notice we can't just plug in 1 because it gives us a 0 in the denominator. So for something like this, I would make a table of values. Just see, okay, what happens on the left-hand side of 1. For all of these, I would just make tables of values. All right? So the limit as x approaches 1 from the left, the y values are getting closer. They're going off to infinity, right? As x approaches 1 from the right, they're going off to negative infinity. Since the left-hand limit goes to infinity and the right-hand limit goes to negative infinity, then the limit as x approaches 1 does not exist, right? Okay. And then something similar here. As x approaches 2 from the left, it's approaching 5. As x approaches 2 from the right, is also approaching 5. So then we say that limit is 5. And then as x goes off to infinity, y gets closer and closer to 6, right? So just as a review, we say the limit of a function f as x approaches some number a is written. The limit as x approaches a of f of x is L. This means that as the values of x approach a, the corresponding values of f approach L. The value of L must be a unique finite number. A left-hand limit is written, the limit as x approaches a from the left. You see that minus there of f of x. The value of x approaching a from the left, and that is x is less than a. A right-hand limit is written in the form x approaches a from the right of f of x. The values of x are approaching a from the right, and that is x is bigger than a. If the left-hand and right-hand limits as x approaches a are not equal, then the limit does not exist. On the other hand, if the left-hand and right-hand limits are equal, then the limit does exist. A limit as x approaches a of f of x may exist even though the function value f of a does not exist. So we saw an example where it was not defined at that point, but the limit did exist. The limit as x approaches a of a function may exist and be different from the function value of f of a. And then graphs and tables are useful tools for determining limits. Okay. So hopefully that wasn't too terribly bad. Yeah, and I'm kind of just being comfortable in the presentation because it's a recording. You can always go back and either change the speed of the recording, either slow it down, or you can pause it at your leisure, or you can even speed it up if I'm not talking fast enough. But I do like doing pre-recorded lectures because then I can flow with it, and then we can use class time to just ask questions and work on homework. So I do intend to use class time as like office hours, and I intend to get as many of these lectures done in advance as possible. Um, our rhythm might be a little bit accelerated. Like I'll probably be doing like 2 of these sections per, like for instance, just basically 2 sections per meeting. It's not always going to be like that, but we need a good amount of them where we're going to be doing double lectures. Okay, so hopefully that was okay for you. On that note, we're going to end the session here, and from one beautiful mind to another, enjoy the rest of your day. Peace.